starting the live stream now.
I'm looking at it on the second screen. It hasn't started.
Okay, thank you. So there should be like a 20-second delay, I believe. It may take a few seconds for that to start.
I see you.
All right, great.
Yep.
Looks like we're live then. All right, I just had to mute that on my screen. That came up on my screen as well. All right, so welcome everyone to the Pi Mu Epsilon induction for 2021. Good evening, students, family, guests, and faculty. Welcome to the annual induction ceremony of the New York Lambda chapter of Pi Mu Epsilon, the National Mathematics Honor Society. I'm Dr. Matthew Jura, and I'm the faculty moderator for our local chapter. Thank you all for being here for this very special evening. I'd like to begin by inviting our Dean of the School of Science, Dr. Janet McShane, to make some welcoming remarks.
Thank you, Dr. Jura. Good afternoon, everyone, and congratulations. Congratulations to the students for being inducted into Pi Mu Epsilon, to the teachers who have guided and inspired them, and to the families, your parents, siblings, grandparents. These were your first teachers and mentors. Today, you are being inducted into Pi Mu Epsilon, the Mathematics Honor Society. You are joining a long list of inductees from Manhattan College. And our Pi Mu Epsilon members have been some of our most successful alumni. So inductees, you're joining a good group. As I look at the list of inductees, and as you will hear later on, the majors of the students are not just mathematics, but also various engineering disciplines. And the list of current members has even more disciplines represented. This reinforces what we all already know, that mathematics is the language of science. And in fact, Carl Friedrich Gauss, a great mathematician, is claimed to have said, mathematics is the queen of the sciences. This is a powerful statement, but what is mathematics? The dictionary states that it is the abstract science of number, quantity, and space. It goes on to state that mathematics may be studied in its own right, pure mathematics, or as it is applied to other disciplines such as physics and engineering, applied mathematics. A different definition states that mathematics is the study of numbers, shapes, and space using reason, and usually a special system of symbols and rules for organizing them. I think our inductees will agree with both of these definitions. In their coursework, they have dealt with numbers, abstractions, shapes, special symbols, rules, etc. The importance of mathematics goes back very far in history, back to Syria and Babylon in the West, and simultaneously in the East and the Americas. Interestingly enough, written records of humanity have records that show counting items before written language. Thus, the need to count superseded the need for a written language. Mathematics has come a long way from just counting or accounting. It underlies every function of our lives, and particularly of our technological era and scientific learning. We have an enormous array of tools in mathematics that enable us to solve fundamental problems in science. We live in an astounding age of advances. Engineers can land a car-sized rover on Mars. Physicists probe the essence of all matter. And we can communicate wirelessly on a vast worldwide network. Underlying all these modern wonders is something deep and mysteriously powerful. It's been called the language of the universe, and perhaps it is civilization's greatest achievement. It is mathematics. Can you tell that I'm passionate about mathematics? The stories of mathematics reveal it to be a creative endeavor done by real people who struggled to discover the underlying patterns of nature on which we have built our modern world. Our inductees can be proud that they are part of this whole process. The fact that you are being inducted into this and other honor societies recognizes your hard work, your dedication, and your ability to perform abstract thought processes. But most importantly, this signifies to us and to you your ability to excel in the future. When you left high school, you thought that was an ending, but that was just the beginning of a new experience awaiting you here at college. And now this is the time to consider what your new experiences in life will be. College gave you a foundation, and now the rest of your life will be an application of the knowledge and skills you have acquired here. May you continue on your learning experience, and may your knowledge empower you to bring change to the good of society that we live in. I wish you all the best and most rewarding experiences to follow. Again, congratulations and thank you.
And thank you, Dean McShane. It's now my pleasure to introduce tonight's highly esteemed guest speakers, Rachel Roca, Robert Valley, and Richard Goldstone. Rachel Roca is a member of the class of 2021 here at Manhattan College and a current member of our chapter of Pi Mu Epsilon. A recipient of the prestigious Goldwater Scholarship and a member of Phi Beta Kappa. Rachel will graduate with a major in mathematics and minors in computer science and Spanish. In the fall, she will begin a PhD program at Michigan State University. Robert Valley earned his undergraduate degree from Manhattan College in 2006. He earned his PhD from the CUNY Graduate Center in 2013 and then returned to Manhattan College as a faculty member. In addition to his published work in hyperbolic geometry, Dr. Valley also contributes to the media highlights column of the College Mathematics Journal. Last month, Dr. Valley was awarded tenured promotion to associate professor, which means he's now stuck with us. Richard Goldstone retired from Manhattan College in 2018 after serving the college for 20 years. His formal training is in algebraic topology, but he's also made contributions to algebraic graph theory. However, he might be more famous as a pioneering rock climber who made the first ascent of the thin face climb Farewell to Fingers in the Shawangunk Mountains. Currently, Dr. Goldstone is enjoying his emeritus status and sharpening his photography skills. Together, this impressive group recently published an article in the College Mathematics Journal titled "The Shortest Paths on Cubes." Tonight, Rachel Roca, Robert Valley, and Richard Goldstone will speak to us about The Spider and the Fly on I-Cubed by Team R-Cubed, a report from our cubicles on a long incubated idea. Please welcome our speakers.
Thank you. Is my screen sharing at the moment?
Yes, it is. Looks good.
Oh, good. Okay. Well, thank you, Dr. Jura. Welcome, everyone, and congratulations, inductees, on your achievements. I'm Richard Goldstone of Team R-Cubed, and I'm going to make a few introductory remarks about our presentation. As you can see, the three R's here come from the first letters of our first names. I'm an emeritus professor at Manhattan College. Rob Valley is an associate professor, and Rachel Roca is a graduating senior. If I may, I'd like to say a few words about why we are here. There's an old joke in mathematical circles about a eulogy for a professor. The eulogist addressing a somber and grieving crowd, begins with, Dr. Jones was a devoted husband, a loving father, and a pillar of his community. He also discovered some wonderful theorems. For example, let phi upper star be the adjoint of a bounded operator on a Hilbert space H, and let M be the orthogonal complement of a closed subspace. The point of the joke is that when important events happen, mathematicians celebrate by talking about mathematics. So this induction is an important event. And so here we are following hundreds of years of tradition by presenting some mathematics to help you celebrate appropriately. Now, as it turns out, this slide came up a little prematurely. This is also an occasion for multiple celebrations. Team R cubed is genuinely remarkable in that it is a 3-generation collaboration, all from Manhattan College. Now, I don't mean 3 generations in the sense of ages, although sadly for me, that's also true. But I mean 3 generation as in Rob was my student at Manhattan College and later a faculty colleague. And now Rachel is his student and our research colleague. I dare say that this is an exceptionally rare event in academia. And if I may put in a plug, which is preaching to the choir here, I suppose, it's a testimony to the kind of education Manhattan College offers. A third cause for celebration is that Team R cubed has had some success in the world of academic publishing with work that traces way back to the original Goldstone Susie Valley student project when it was only Team R squared. That article was published in this issue of the CMJ. And then the second article by the now prodigiously fortified Team R cubed just appeared last month also in the CMJ. So the details of what we've been up to are of course set forth in the pictured articles, and we'd like to try for something a little different in our talk. We like to pull back the curtain that hides the nature of mathematical research from view and give you, well, just a peek at what's involved in an activity we find so engaging. We do this understanding that the research experience is in certain ways different from the classroom experience. And of course, we hope that some of you might be intrigued enough to to try it some more, investigate some more. So the story begins, our story here, in 1903, when a noted puzzle maker, Henry Dudney, published something called the spider and the fly puzzle. Here's the original diagram. This is the cover page from Dudney's book, and this is the original diagram. And in this puzzle, the spider is at point A over here, and he has to get to the fly at point B along the shortest possible path, but the path has to be on the walls, the floor, and the ceiling. The spider, you can't go through the middle of the room. You have to stay on the walls and the floor and the ceiling. So the problem is to find let's stay there for a moment. The problem is to find the shortest path that the spider can take. So about 100 years later, over here on this timeline, but still before I was at Manhattan College, actually, I was tasked with observing an adult extension course on critical thinking. The presenter gave Dudney's puzzle, and I'm sorry to say without attribution, and gave the audience maybe at best a minute or two to come up with a solution. And then with a flourish, ta-da, the critical thinker revealed a solution like the one here from, this one's actually also copied from Dudney, and quickly moved on to the next demonstration. Well, the clever idea, as you can see, I think, is to slice open the rectangular solid, unfold it out flat, and draw a straight line from A to B, which is, of course, being a straight line, it's the shortest distance between 2 points. And so this must be the shortest possible path. I have to say, sitting at the back of the room, that I thought at the time that this was an example of a failure of critical thinking. There are clearly many ways you could slice open and flatten this thing. How do we know that this particular unfolding that is displayed is actually produces the shortest path? And the answer is we don't know that. A proper analysis would have to look at all possible unfoldings. Well, see, Dudney understood this too. And his published solution showed all the possible unfoldings. I just showed you this one over here, number 3, a moment ago. As you can see, number 4 is shorter. It's better than number 3. And number 4 also has some other features that I hope you will perhaps remember a little later in the talk. So one is, this is the shortest path. It's only slightly better than number 3 by a very small amount. And that fact has some significance for later on. And I'm sorry, just keep jumping. And the other thing is that it is a 5-face path. 1, 2, 3, 1 here, face here, 2 here, 3 here, 4 here, 5. The best path actually uses 5 faces of this solid. And the obvious ones that go across the floor or the ceiling, which are considerably longer, only use 3. So these ideas sat around in my messy cerebral attic until I had a chance to dust them off and suggest an undergraduate summer research project to Rob. So of course we couldn't just resolve Dudney's problem, so we opted for something which would be perhaps a little bit more challenging. So first we chose a cubical room. Now the cube has more symmetries than a rectangular solid, and that adds possibilities that have to be dealt with. And secondly, and this was much more significant than what Dudney did, we allowed our spider fly locations to be anywhere on the opposite faces. Dudney had his very specifically anchored in very symmetric positions with respect to each other. And we said, nah, they can be anywhere now at this point. We'll let them be anywhere. So it's a new situation, but it's the same problem for given spider fly locations. What's the shortest path and how many faces does it traverse? So the first obstacle to answering this, if we're not going to imitate the so-called critical thinker, is that we have to enumerate all possible cube unfoldings. And that was what I approached Rob with, and he is now going to take over the discussion if I let him there.
Thank you, Richard. So here we are now back on the timeline. We're in 2005. I'm just a shy junior math major at Manhattan College. Not really sure what I wanted to do after I graduated. I had been considering graduate school, and I know I've enjoyed my math classes thus far, but I wasn't ready to make that decision. So Richard comes along and proposes this research project, which included counting unfoldings of the cube. I'm simultaneously excited and nervous. And when we first get together to begin the project, he tells me that I should be spending about 5 to 6 hours per day working on this problem. And he had me working hard. Here are some pictures from my original notebook from that summer. At first, I was reading through textbooks, learning the math background needed to be able to approach our problem. And I wasn't just casually reading, I was working through most of the exercises at the end of each section. You can see that on the left-hand side, you've got some definitions and theorems. On the right-hand side is my exercise work. And after several weeks, I was armed with some new techniques ready and excited to attack the unfolding problem. And it was really hard. You know, I often spent days making little to no progress at all. What you're looking at here now is a little bit later in the summer, some computations on the left. On the right, I was trying to write out some proofs. And if you look close enough on the right, Richard's giving me some feedback in the margins, giving me some edits on my proofs. And, you know, in addition to working on the problem every day, Richard and I would meet once a week. I had a fantastic time meeting with him for pretty much the whole day. We talk about the work and think of new plans of attack when I was stuck. And I'm happy to say that finally, after 2 months of working on this project, I had a breakthrough, my aha moment, eureka. And I will never forget it. First of all, no, I was not in the shower. But funny enough, I was in the DMV waiting for my friend to take her driver's permit exam. So I knew I had plenty of time on my hands. All of a sudden, I'm sitting there writing down some computations that I had done a million times, and the solution came to me. I realized what I needed to change. For the remaining 2 hours that I was still waiting, I had a huge smile on my face, which is, of course, not your typical expression at the DMV. I definitely got some looks for the excitement I was showing. And so here is the result. It turns out that there are 11 distinct ways to unfold a cube. But what I really want to comment about here is actually that this result has been known for a long time, but we proved that there are 11 unfoldings in a novel way. And to some of you, this might seem like a futile endeavor, but in fact, it was anything but that. Now that I've had some time to reflect back as a faculty member, Richard's plan for me to enumerate the unfoldings had so many important aspects of a good undergraduate math research project. It was an easy problem to state. It had me reading and learning mathematics outside of class material, but definitely related, as you saw in my first set of notes that I showed you. Something that I'm not going to get a chance to speak about right now, but was a key feature of it was that it combined techniques from several areas of mathematics, really helping me see connections from different classes and different fields. And lastly, as you saw in my second set of notes that I showed, you know, you could start with some examples, get your hands dirty, and then generalize to sort of prove some things. But as I was just saying, the mathematical details of this project are for another day. So moving along a little bit, that following winter in 2006, I presented our results at an undergraduate poster session at a national conference called the Joint Mathematics Meeting, or JMM. And I'm a little embarrassed that I still have it, but here is my original poster board, which is sitting in my office 15 years later. It's wilting a little bit, but what I want to mention here is that during that conference, I met many other undergraduates there who had the same passion and excitement for math as I did. And that conference, along with my impactful summer research experience with Richard, really helped me solidify my decision to go on to graduate school to research mathematics. All right, so we're going to jump a few years now. So fast forward 7 years to 2017. I was incredibly fortunate enough to return to Manhattan College as a faculty member. And by the way, Richard and I hadn't discussed our work in all of those 7 years while I was working on my PhD. After a year of me getting used to full-time teaching, we decided it was time to revisit our work and write an account of what we had accomplished with the unfolding side project. But in addition to that, we would also revisit that original shortest path problem we set out to solve. So I'll also comment that the writing of our work on the unfoldings wasn't easy. After many, many rewrites, we were finally successful in publishing our work in 2019. So I'm going to pause there with the history. And I want to get back to that shortest path problem that Richard was talking about, but now equipped with the complete set of 11 unfoldings of the cube. So let me just remind you, we're considering a cube instead of a rectangular prism, and we're allowing spider and fly locations to be anywhere in the interior of opposite faces. So for given spider fly locations, I've picked some out right here. We want to know what's the shortest path and how many faces does it traverse. And what we've also drawn in is a couple of the paths that we might consider to be the shortest path, just to help you visualize a little bit. And with that, let me send it back over to Richard, who is going to tell you about an operation we can perform on those 11 unfoldings and how we made good use of them.
Thank you, Rob. Team R squared came up with the concept of corner moves, which I'm about to illustrate for you. We came up with the idea as a way to generate unfoldings, because that's what we were doing way back. And the work on cube unfoldings actually showed us that we could get all possible unfoldings could be generated by the corner moves I'm going to show you, starting from any one particular unfolding. So you could sort of get them all no matter where you started. So then many years later, when Team R cubed returned to the field of battle, we realized, and this is a feature, I think, of mathematical research, we realized that the corner moves that we had used for one thing were actually good for more than their original intended purpose. They could be used to detect whether a path in a given unfolding was optimal. And if it wasn't going to be optimal, the corner move, we could replace it with a shorter path by altering the unfolding. So here is a four-face path, 1, 2, 3. Here's a four-face path that a corner move replaces with a three-face path. That's the corner move, like that. And this three, if you look at the original and the subsequent one, you can see that the corner move has given us a shorter path. So this raises the question for us of whether, without performing a corner move, we could predict from the geometry whether or not a corner move would give us a shorter path. So, okay, so put some extra lines in that relate the situation to the pivot point where the corner move is happening. Throw away all the extraneous things. So you just have the two paths and those additional lines. Focus on the two triangles here. And now I'm showing you basically a picture from the paper. So this picture is just a little bit different in that the corner move is going up here. So the things I just showed you, the corner move went from right to left. In this one, the corner move is moving from bottom to top, but the two triangles are the same, and they're what we want to focus on. And this triangle over here has two sides the same length as this triangle, right? They have the side in common, and they have these two legs, which, because they come from the 90-degree rotation in the corner move, are congruent. So the third sides are the original and the new paths, right? And which path is longer then depends entirely on which of these two angles is bigger, whether theta is bigger than alpha. So I've already put down here, I mean, there's a small bit of mathematics. These three angles add up to 360. So theta plus alpha adds up to 270. Now, if this theta and this alpha are equal, then those two triangles actually congruent. The original path and new path are the same length. So what happened is we did a corner move, we got a new path, but it's the same length as the original path. If this theta here is bigger than this alpha, which means it's bigger than 135, then the original path is longer than the new path. In other words, the corner move has shortened our path. That's kind of what we're interested in. And if this theta here is less than this alpha, then the original path is shorter than the new path. In other words, the corner move has made our path longer. That's not something we hope to encounter, although it's useful to know it. So what we got here, so in another thing in mathematics is you get to make up names for things. So this angle here you go from the source point to the pivot point to the target, this angle theta we call the decision angle. And what I just told you is that if the decision angle is less than 135, the corner move shortens the path. If it's equal to 135, the corner move gives you a same length path. It's a different path, but it's the same length. And if it's greater than 135, the corner move lengthens the path. Now, this understanding that came, these insights that came from corner moves had immediate and I think profound for the work that we did consequences. So here is a piece of a cube unfolding that would be involved in a 5-face shortest path. You would start with a source point over here in the shaded region, and your path would run through 5 faces here into a target point in this other shaded region. And if you think about this diagram a moment, you can't stay inside this particular configuration if you don't start in the lower left shaded region and end in the lower right. You can't start down here, you'll immediately run out of bounds. So the source point region is this shaded region, the target point region is that shaded region. And here is the situation for it. So you pick it, here's an arbitrary starting point, source. Here's an arbitrary target. This line from source to pivot to target is the angle. These two lines define the decision angle, and bingo, this black thing here is a 135-degree angle. If you look at this, you'll see that no matter how I choose the source point, and no matter how I choose a target point, this red thing here is going to be bigger than 135. So what does that mean? It means that a corner move is going to shorten it. And what does that mean? It means a no 5-face. It means that there are going to be no 5-face shortest paths. If there is one, bang, we'll hit it with a corner move. We'll get a 4-face shortest path or something else. So only 3- and 4-face paths are candidates for shortest paths on cubes. There's no way without giving you details to tell you how much of an advantage this proved to be to us by eliminating the fact that 5-face paths, which remember, Dudney had a 5-face path when he wasn't dealing with a cube, that we didn't have to deal with them as well. Now, the critical thinkers among you are now thinking to yourselves, how do you know that a particular configuration like 1 up and 3 over and then 1 up, how do you know that is the only configuration that gives rise to 5-face paths? And the answer to that question is because Rob, he already figured out all the unfoldings, and we were able to look at all of those unfoldings and see that there were generic configurations for each of those paths, for 3-face paths, 4-face paths, and 5-face paths. So this really is generic. It could be rotated or reflected, but it's going to be essentially congruent to this, any 5-face path. So then something not so good happened. Also a feature of research. Here's a 6-face path, right? Actually traverses 6 faces. So, oh, by the way, the argument I gave you also works for 6 faces. So here we go. We got this whole system. We've built this whole edifice, this carefully constructed edifice, and we do our corner move to get a 5-face path. Well, can you see what went wrong here? It's like, ah! Because all of a sudden, oh man, sorry about that. All of a sudden, I got to get back to where I was. No, I'm sorry. Yeah, too bad about that. All of a sudden, we have this path going outside the boundaries. It's leaving the boundaries, and that means it's not a legal path. And that means we were saying we could always shorten the path, but we didn't realize that some of those corner moves were going to shorten the path and give us something that isn't legal. So the scream is appropriate here. This, yeah, you saw the other image, unfortunately, but this carefully constructed edifice that we built with everything fitted together perfectly is now crumbling before our eyes because of this. And what we're left with is the possibility that this is what we've built. So as I say, this is something that researchers have to deal with. It happens all the time, really. And of course, what you do when life gives you lemons is the usual thing. Everyone knows what you do when life gives you lemons. You cut them in half and squirt life in the eye. So in pursuit of that particular goal, here's that picture again without Monk's scream and the redness there. This is the bad path. So the thing that we did was we said, well, maybe we shouldn't call that a bad path. Maybe we should treat that like any other path. And if we're going to treat it like any other path, then what do? We just do corner moves on it again. Well, okay, we did a corner move on it again. Then you can see the lemon is not happy because it's still a bad path. It's still outside of the boundaries of this unfolding. But now that we've agreed, we're just going to treat it like one of the folks. We can do a corner move again, and this time we get a path that is inside all the boundaries. It's a 3-face path in this case. It's the shortest path. And we're back in business. That original 6-face path, which looked like it was going to be, we looked like we couldn't deal with it the way we had been talking, ends up being a 3-face path that's shorter. So what we learned about this is that we don't have to color inside the lines, right? And we now have the law-abiding paths which stay inside the unfolding boundaries and behave themselves, and we have the renegade outlaw paths, which are newly dignified with the title of pseudo-paths. That's what we call them. These things are pseudo-paths. And these things wander outside the unfolding boundaries and create all kinds of havoc, except they're both welcome at this point, because if a corner move produces a pseudo-path, so that's the thing, that 5-path thing I showed you, we got a pseudo-path, then we can just keep going with the corner moves. And a fact from geometry, which I haven't showed you and won't display here, is that we found that the decision angle of a pseudo-path is always greater than 135. So anytime you get a pseudo-path, it can always be shortened by a subsequent corner move. So if you do a corner move and you get a shorter law-abiding legal path, then good, you shortened your path. And if you get a pseudo path, then you just keep doing corner moves, because as you do those corner moves, the number of faces traversed decreases, and eventually you're going to end up, if you don't stop before that, with a 3-face path, and it will be shorter. So you can always shorten the 5-face path the way we originally thought before we had trouble in paradise. And this means that our 5-face path argument is rescued for the reason described there. So now what we know is that we only have to analyze 3- and 4-face paths. I say it's a tremendous advantage technically, as it turned out. but there's still an issue about how do we collect all these possible paths and so that we can look at them in one place, right? And compare them. So here we had to introduce another notion, the unfolding grid. So what you're looking at here is the cube placed on the floor and viewed from the top. So you're looking at the cube from the top down. And what I'm going to do is slice it open in all possible three-face ways, right? So we're going to go like this, right? So this, now you should think of this as the floor of the cube. This is the former east wall, and this is the former north wall, and this is the former west wall, and this is the former south wall. And these four things all represent the former ceiling, right? So you can only have one of these at a time, but if you have a shortest path that starts here and goes out to here, then it started on the floor and went across the east wall and ended up on the ceiling. But if you went this way, you started on the floor and went up the north wall to the ceiling. So that's all three-face paths in that grid. Then we're going to add in our generic four-face path configuration to that, and that gives us this grid. And then another four-face path configuration that gives us this grid. And this quadrant here now has all possible 3- and 4-face path configurations, and we don't have to think about anything more, right? Only 3- and 4-face paths. So otherwise we'd have a much bigger and more complicated grid to look at. So now I can do the same thing in the other 3 quadrants, and that's what we call the unfolded grid. That's basically, in that grid is all possible 3- and 4-face paths that you can get. Once you choose, you have to choose a source and target, of course. So if you choose a source point, which is this S, and a target point, which is this T, and you perform this process, so what happens is that I'm thinking of the S as staying on the floor and the T as being projected out to all of these. The T was on the ceiling, and everything around here is a copy of the ceiling. So this shows you all the possible 3- and 4-face paths you could get with this particular source and this particular target. I mean, you change the source and target, it's going to look different. And the 3-face paths you can see are, the notation's pretty clear, right? You go right twice, you get over here. If you go right and up and right, you get over here. The dotted paths turn out to be, if you look at them carefully, pseudo paths, so they're not going to count. So this one, for example, over here goes through a pivot point, so that isn't going to count. But this gives us everything, and this isn't a sketch. This is computed. We computed these things. So how was it computed? Well, what you do is you go back to high school and you put an X and a Y axis into this thing. It's the comment is false. It's not always wise to coordinatize. I just like the rhyme, so I put it in there. But we put axes in here, and we pick some. Now we have coordinates. The axes ran, I think, right through the middle. We have generic coordinates for the source point and generic coordinates for the target point. The difference in letters is meant to suggest that we're going to keep the source fixed and and vary the target point. And then when we have coordinates, we have, we wait for a miracle, and the miracle typically, in this case, is algebra. And I might add high school algebra, sort of fancy, but just high school algebra. We compute from those coordinates all 12 distances. All 12 of the lengths of these distances of paths and pseudo paths. And you can see here, here are the things that label the ones you saw before. And these are the squares of the distances, by the way. And those of you who are familiar with analytic geometry can see these sums of squares things look kind of like the distance formula. That's what they are. This is a distance formula. So, have we now solved the problem? Have we not, is it time to pack up our tents and slink off into the night? Well, a perfectly good answer would be yes. you give us the positions of the spider and fly, we plug those coordinates into the formulas, we get 12 answers, we throw out the pseudo paths, and we pick the smallest one, and we're done. Or ones if there's one, right? So we can find the shortest path. We did it. Yeah, well, except meh. Why meh? Well, first of all, machine computations would be needed to do this. And round-off error would make the decision impossible when the paths are nearly the same length. Remember when I showed you the Dudney path, the optimal one was only slightly different from the other one. You'll never be able to distinguish in many cases between various paths because they'll be too close together, and the precision of your computation won't be able to tell you about it. So a much more important thing, however, is that we don't really at this point have any sense of what it is about the location of source and target that force a four-face path to be optimal. How come four-face paths happen? Why don't you always use three faces? Why don't you just use the floor or the ceiling? Why do you have to mess around crossing walls and whatnot? So let's take those formulas now that we wrote them down and try to get a geometric insight for that. Rob is going to show us how to do that. If I let him. There we go.
Great, thank you, Richard. So we put all of those distance formulas that Richard had just shown you into Desmos. And for those of you who don't know Desmos, that's the program you're viewing right now. It's a free online graphing tool. And so what you're looking at is the same unfolding grid. In red here in the middle, you have the source point. Remember, that's on the floor of the cube. And then in this blue one in the center square represents the target point, which is on the ceiling. We've just projected it down. And for the moment, I'm just showing you 2 of the 12 possible unfoldings. This are possible paths. This orange path is a 3-face path, and the green path is a 4-face path. And this is actually one you can get from the 3-face path to the 4-face path using the corner move that Richard had shown you before. What's a little different from the diagrams Richard was just showing you, you'll notice we've put circles in so that you can more easily determine which is the shorter of the 2 paths. Maybe I'll zoom in a little bit. At the moment, with this source and this target, the green 4-face path is shorter. And what's cool about this is that now we've entered everything, and Desmos is handling the change in target or the change in source, and you can see the resulting paths. And so where I've stopped it, now this 3-face path is shorter. But with that, we want to look at all 12, right? That's sort of the point. And let me back out a little bit for a second. So now you're looking at all 12 possible paths. The orange ones are the 3-face paths, and the green and purple are the 4-face paths. And I'm going to zoom in again for a little bit. So hopefully you might be able to see, hopefully it's zoomed in enough, but I'll let you know what's happening. For this source and this target, a green 4-face path is shortest among all of them. Okay, you can kind of see that the green circle is sitting within the orange one. And, through this Desmos visualization, a couple of things became clear to us. First, although the visualization was nice and we can play around, and I'll move the target in a minute again, it was still not enough to determine the shortest path, which, as Richard mentioned, when differences in path lengths appeared to be minuscule. And second, it appeared when you start to play around with this, so I'm going to move it again. Here now, again, we have 3-face paths. There's an orange path that's shortest, and that seemed to be happening a lot. So it seemed these 4-face shortest paths might be more rare. than three-phase shortest paths. And what we wanted to do is discover more precisely when this would occur. When would we have a four-phase shortest path? And from playing around with Desmos a little bit, I'm going to try to bring it back to the configuration I had before. Here we go. It appeared that if you were closer to the corners for your target, you were more likely to, or at least that's when a four-phase shortest path might show up. And this led to a shift in our objective, actually. So, and that's another common feature of mathematical research. We were no longer concerned with finding the shortest path for a given source and target. Rather, we were now interested in the following. If you're given a source point, can we identify regions of target points which corresponded to four-phase shortest paths? Like this specific point is 1, but we wanted to know if there were regions. And we were really excited about our new direction. But at this point, R squared realized we needed more help, possibly from someone with some programming background. And with that, I'm going to send it over to Rachel.
Thank you. So here we are now in our timeline. So we're almost here. And it's the winter of 2019, which was my sophomore year, when I joined Team R squared to make it R cubed. So I was already somewhat familiar with this project since in the past I had helped read over and give some comments on the R squared paper that was talked about before. And so interestingly enough, but very sadly, I have never had a class taught by either Rob or Richard. But Rob is my academic advisor, and I had worked with him my freshman year in that spring semester on oscillation and continuity of functions at points that use some MATLAB animations. And that was super fun, and I learned a lot, but it was very different than this type of problem. So the project last year was mostly expository. The proofs we examined were already well known and written, and I was just adding a little bit of visualization with some MATLAB to functions that we knew about in those proofs. But this was research, and we didn't know what was going to happen. So I was thrilled and scared to join the team, and I had no clue if I'd be able to provide anything useful. But to this day, I am still very grateful that they thought of me, and that the semester before I had decided on a computer science minor. So, here we go. Okay, so here's me giving a preliminary, more traditional math talk at the Mathematical Association of America's Metro New York section meeting. And you can see that I'm presenting on Desmos, which Rob just walked us through. And so this was my second ever conference, and I was very excited and nervous. Rob, being the amazing mentor and advisor that he is, snapped this picture, but he also took another one of me looking like I was eating a figure. And that figure we'll see in a few slides, but due to the limited dignity I have left, we're just going to stick with this picture of me. And I refrain from adding the picture of me eating a figure to the talk. So while I've been to many more conferences now, both presenting and just listening, the excitement hasn't gotten old. And conferences are a great way to connect with both people and new ideas in the math community. And so I highly recommend for all the students here to try to attend as many as you can. And I know networking is such a buzzword, but actually at the joint math meetings this last January, which was the same conference that Dr. Susie Valley presented in all those years ago, I actually met one of my future advisors for the program I'll be joining at Michigan State University. So that was cool. But anyway, let's get back on topic. And so at this point, I had only had experience writing programs in C++ and MATLAB. And so if you know anything about those two programs, I naturally chose MATLAB. And in a somewhat brute force approach, the code takes in the position of the spider, the source point. And then it works through a fine grid of flies. And so it calculates the shortest path between the spider, which each point on the grid, which represented the fly or the target point. And so the fly point is then given a color based on what that shortest path would be, 3 or 4 faces. And so this wasn't really elegant, but it did allow us to get some sort of visualization. And as we saw with Desmos, moving things around was a little bit finicky because we couldn't get regions and there were lots of lines and circles. And so finding anything beyond a specific point was a bit of a hassle. And so here, for this MATLAB code, the user only had to input a source point, which is in the form of a coordinate, to get some visualization. And so here is an example of one of these visualizations with the spider or a target point in this cyan point right here, around 0.6, 0.6. And so you can see that there are a lot of colors in this, and this was the figure I was eating. But the most important color is the blue. And so the blue dots here and here represent the 4-face shortest path. So the shortest path between the fly and the spider goes over 4 faces for the flies located here and here. And so the other colors have names and definitions that Richard created to help explain different phenomena. For example, these different boundary points meant different things, but no one in Team R Cubed really remembers them completely, and they didn't end up in the paper. And so this is to say that the work that is published in paper is only a fraction of the work that's actually done. And research is uncertain by nature, so sometimes you go down different paths that aren't necessarily helpful in getting where exactly you want to go in the final step. And so this was really nice to see, but I quickly found a bug that was not so quickly understood. In fact, it took several months to correct. And so if you think about the computer science classes we've taken, you know, even in a final project when you have a few weeks, imagine this computer science project taking months and spending most of that time figuring out the bug. And so Richard originally finally figured it out, but we all looked at it in R Cubed, including Dr. Angel Pineda, Dr. Mark DeBonis, and even Dr. Tina Tien in the computer science department. And the issue came down to exactly what Richard was explaining before with numerical approximation. And this was due to the numerical precision of MATLAB, and that at certain points, it just wasn't able to give us a correct answer. And this is all just approximation. And so we see that technology is great, but it has some unexpected consequences that you need to be aware of. So these are the formulas that Richard used in Desmos and that he had shown before, and I had used in the MATLAB to calculate the distances in the shortest paths. And so we see that if a particular path is shortest, then its distance will be shorter than all the other paths we see here. And in this way, we can make inequalities with them. And these inequalities just compare the different lengths. And so actually, we don't need 11 inequalities to compare all of them. I won't go into why, but you only need a few. And so Richard came up with the great idea of using these inequalities to make plots, which was similar to what was done in Desmos. And so using these inequalities, we no longer would have to brute force our way through a grid, which when the grid was really tiny, took a bit of time. And so these, when we make the inequalities with these different distance formulas, it's not nearly as scary as they look, because what ends up happening is the x squareds and the y squareds cancel, and so we get a linear inequality. So here we have 6 examples of this. And so in all these dots here are our spiders, and the shaded regions are where the fly would be located to create a 4-face shortest path in each of these figures. And so, like I said, these plots are based on the inequalities we can make from the formulas previously shown and not the grid. And so Rob, Richard, and I all solved the inequalities by hand to check, but it's nice because with technology, we don't actually have to calculate them. We let technology do that for us. And so it's worth noting that these plots were not made in MATLAB, but they were made in Sage. And Sage is a free open source mathematics software. And Richard and I hadn't used Sage before, so there is a bit of a clunking around experience. So you might be wondering, why did we bother changing to a different software? And MATLAB, as wonderful as it is, it has a special place in my heart. It's not open source. And so if we wanted our work to be accessible to everyone, and I think such a cool aspect of this project is that it can be, right? The mathematics isn't super complex. A high schooler can compute these lengths, and it has a nice visual feel to help everyone see it. But we need code people can run, and code people can run freely is a great touch. And so in our paper, we have several pages in the index that are dedicated to all the code and further explanations of how it works. And we also see a trend now of researchers posting their code on GitHub, so their work can be used in further exploration and replication. This is something that I have taken advantage of and have been very grateful for in the current research I'm doing in neural networks. But because of this open source nature, if you all wanted to, you can play with the code yourself with the links that we have for all of these figures, and you can move them around. And a super cool thing about this is we see, as Rob pointed out, that these regions look very different depending on where the spider is located. And so we see sometimes there are barely any four-face shortest path regions, and other times they can take up a large amount of the face. And these can come in all different forms, right? They're always anchored to the corner, we notice. They look like triangles most of the time, but we can see other different polygonal figures. So these were the last plots I made for the project, which ended the research work of shortest paths for Team R cubed. And we went back to MATLAB and again relied on the grid, and I'll explain why. But these plots were a really nice culmination because basically they tell us the probability for each potential spider on the face that the shortest path to a fly will be over 4 faces. Now, theoretically, this probability is computed by looking at the area of the regions of the 4-face shortest paths, and then you divide that by the area of the whole face. We settled for approximations with this. So in reality, what we did is calculate the probability by the area of calculating the number of blue dots we saw in the previous figure that I shown, divided by the number of total dots in the grid. And so that included the blue dots, but also the white dots that you didn't see that represent 3-face shortest paths. And so here on the left, you can see a 2-dimensional contour plot. And on the right, we see the 3-dimensional probability distribution version. And so you can note in either one you decide to look at is that when the spider is in the middle of the face, the probability that there will be a 4-face path to a fly is very low. But as that spider decides to crawl into a corner, regardless of a corner, that probability goes up significantly. And so there's still some things about this that we don't completely understand. Specifically, there's some asymptotic nature in these corners, but this seemed like a good stopping place for us. And so it's worth noting that most times in research, you just simply can't answer every single question related to your project. But as you can see, the single project of the spider and fly has occupied people's thoughts for more than a century. So now at the timeline end, and it is spring 2021. So after lots of rewrites and edits, including my favorite late night emails from Richard when he had added something new or done something different, we submitted a manuscript to the College Mathematics Journal, the same journal that published R Squared's work before, in January 2020. And we are happy to announce that our article is now published in the spring, just a month or so ago. So that's the story of R cubed. And so some parts of our story were left out, and namely those are the proofs. And this is not to say that proofs are not important, but in the spirit of the talk and the limited amount of time we had, we decided it would be best to forego them. All the proofs in that contribute to our work are in the papers we cited and in the paper we have ourselves. And so we hope that some of you who might be interested would want to check those out. And I want to emphasize something that Richard said in one of our meetings for preparing for this talk. He said that proof is the mathematician's laboratory. We try to discern what is going on, but then subject our insights, or maybe they're closer to guesses, to the intellectual rigor of the proving process. This is an exercise that, as often as not, forces changes to our initial ideas, driven by an inability to justify what we thought. And so Rob, Richard, and I really enjoyed creating this talk, sharing stories, combing through some of those old proofs, and just doing some joint reflection of the work we have done. And self-reflection in research is of utmost importance because there's a lot of questions to ask, such as what can you feasibly do? How should you do it? Is what I did right? And where do you go next? And so as we all tried to emphasize, research is a process, and it's hard, it's long, it's not without pressure, and it's pretty annoying at times. So I feel very lucky to have had research experiences through my entire undergraduate career. And I'm excited, but kind of daunted to begin it, dedicating myself to do a lot more of it in the future. And so I know this sounds slightly contradictory to what I just said about research and about how hard and annoying it can be, but there really is something that keeps drawing us back. And there may be no answers in the back of a textbook that we can refer to, but that just makes those eureka moments so much sweeter. So I just wanted to offer up 3 points to take into consideration, even if you aren't a mathematician or researcher or don't plan on becoming one. So one is to collaborate with others. It was amazing working with R cubed, and we were all able to provide different things. And don't let yourself get isolated because that's pretty miserable when doing research, but connect, learn, and grow with others. And tangentially, being open-minded and interdisciplinary can add a lot of cool elements to whatever you're interested, math or otherwise. And just as there are many, many different areas to study math, there are just as many paths to take in life. So self-reflect about what excites you the most and situate yourself to get to that area. I love this research project, but I learned I will probably not be a geometer. Finding your niche makes research and life a lot more fun and a lot less annoying. And finally, the ability to change our ideas when unable to justify them through rigorous examination is not just important for proof writing or other technical fields. This trait carries out in life to make us more informed, open-minded, and accepting. As we are here to celebrate your achievements in mathematics, this is a natural time to self-reflect on your accomplishments so far and what your goals might be in the future. We wish you all success in whatever unanswered questions or uncharted paths that you decide to pursue, mathematical or otherwise. Congratulations again, and thank you.
Well, thank you very much to Team R Cubed for the excellent and very interesting talk. So now would be the time. If anybody has any questions, feel free to, if you're in the Zoom call, please feel free to just state your question. Take off your mute and state your question, or if you'd rather put it in the chat in the Zoom, that's fine. I can relay your question to the speakers. Or for those of us who are in our YouTube live stream, feel free to enter your question in the live stream. So I'll open up now.
I had a question. So it seems like you could consider this problem for any convex polyhedron, right? Is there what's known about doing this game, this fly and spider game, for other platonic solids besides a cube, for instance?
Should I answer that? Well, I would, a couple things. First of all, as you can sort of tell, this thing, the cube pretty much knocked us out as it was. But if, I mean, and not to denigrate your question at all, but it's obvious that we should go on and do at least the other platonic solids. So, but, you know, maybe we will at some point, or some of us will, but we more or less had enough for the time being. The second answer is that people have been very busy analyzing this type of question. Not exactly what we did, but in fact, there was a rather substantial breakthrough, which you may have read about recently, which had to do with shortest, well, geodesics, which are shortest paths, right? On the dodecahedron, which is one of the, which is of course one of the platonic solids. And I'm sorry that I don't have in my messy cerebral attic the names of the authors, but it's pretty recent. There, the question was about finding geodesics. So the closed geodesic. So unlike ours, you had to go around, come back to where you started. And the goal was to find them ones that don't go through any of the vertices. So that's been a substantial problem for a long time and recently solved. So I would say that there are people working on, actually, we didn't even know that while we were doing this, but there are people working on this. I don't know that anyone has done a spider fly type thing for other solids. But maybe somebody will, and certainly the first thing you would do would be to unfold it, right, and draw straight lines. So you would start off the same way, and maybe there are corner moves, you know, I just don't know. We haven't thought about it.
Thank you.
So, you know, I thought that was super cool. And, you know, I hadn't heard the end of the story, but Rachel was alluding to a numerical analysis question about, you know, basically precision, how we store numbers in a computer and how it affected your results. And then you solved it with an inequality. But could you say just a little bit more about what was the issue that, you know, you couldn't, you know, solve in a numerical analysis sense?
Sure, I can take that question. So the cool thing with the cube, and in certain places where we put our spider, is that we get a lot of like symmetric results. And so when I had first noticed, at first I didn't recognize anything was wrong. I was playing around with it and, you know, seemed to run, there were no errors. But when I put the spider in a very specific location, I think it was the center, I noticed that, and this didn't actually come from the 4-phase or 3-phase shortest regions, it came from those extra points, colors that we had in. But I noticed that some points were missing. That shouldn't be, like they were just like splotches. And so that got me pretty worried because I checked over all of my results. Everything was in right. It only happened at some points. And so what turned out is that the calculation was about whether or not something was equal, 2 path lengths were equal. And just because of the precision, you know, it went out so far that there were, you know, minute errors that they were no longer considered equal, even when they should be. And so how I originally ended up fixing it was that I just kind of truncated it. We decided on like some arbitrary but large decimal number, and we said like good enough. So again, there was a lot of approximation involved, and MATLAB got kind of mad with some of all the different functions we were using with absolute value and taking the square root. Like, it all together kind of created this perfect storm that we were able to isolate a few points where things didn't work just quite as it should have.
I'd like to, this isn't quite what you asked about, but I'd like to mention that we were trying to characterize the regions and before Rachel's work. And, you know, we had very, very fragmentary ideas about what they were. And for example, if you know what this means, about the best that we had managed to do was with the regions were open sets. And after Rachel did all of this work, we had a really good idea what the regions ought to look like, and we were able to prove things. So the things that we proved in some sense superseded the approximations, but if she hadn't provided us with those images, we would never have known what to try to prove. So they were absolutely essential. We wouldn't have gotten anywhere without them, even though, you know, they had flaws. They were a critical component.
Thank you.
All right, any other questions for our speakers? I don't see anything in the Zoom or the live chat on YouTube. All right, let's thank our speakers again. All right, so now as we go into the actual induction phase of the ceremony, please allow me to introduce you all to the current president of our Pi Mu Epsilon chapter, Alexandra O'Neill.
Thank you, Dr. Jura. Let me tell you about the society in which my fellow Jaspers are to be inducted tonight. Pi Mu Epsilon was founded at Syracuse University and incorporated at Albany, New York in 1914. The Honor Society currently has over 300 chapters at colleges and universities throughout the United States. The mission and purpose of Pi Mu Epsilon is the promotion and recognition of mathematical scholarship among students in post-secondary institutions. It aims to do this by electing members on an honorary basis according to their proficiency in mathematics and by engaging in activities designed to promote the mathematical and scholarly development of its members.
Chapters of Pi Mu Epsilon may be chartered only at academic institutions whose standards are excellent in all the liberal arts, and particularly so in mathematics. A careful investigation is made before a charter is granted to an institution. Manhattan College's chapter of Pi Mu Epsilon, the New York Lambda chapter, was granted in 1961. Our chapter has the following requirements for membership. Students must either have a GPA of at least 3.2 in any 6 mathematics courses that may be counted towards a major in mathematics, or be currently enrolled in their 6th mathematics course and have a GPA of at least 3.4 in their 5 previous mathematics courses. Moreover, members must have an overall mathematics GPA of at least 3.0 and at least a 3.0 in all undergraduate courses. Applicants must also obtain the recommendation of a member of the faculty of the mathematics department. Upon joining the society, members are required to offer free weekly tutoring in mathematics to their peers at Manhattan College. This valuable service has been a staple of our chapter for decades, exemplifying the Lasallian mission of the college. Over the past few years, our chapter has taken steps to further fulfill the mission of Pi Mu Epsilon. Members have worked on solving mathematical questions from the problem section of the Pi Mu Epsilon journal. A few students have been acknowledged in the journal for their correct solution. In one particular instance, our student was the sole person to solve the problem correctly and thereby had their solution published in the journal. I might add that during the coronavirus pandemic, the Pi Mu Epsilon tutors have continued to tutor in an online fashion. And so we appreciate that very much. So it is now my honor as moderator of Pi Mu Epsilon to begin the induction. I invite the chair of the mathematics department, Dr. Helene Tyler, to lead the candidates in the Pi Mu Epsilon scholarship pledge. And I'll now switch the view to the gallery view so that everyone can see our inductees.
Hi, everyone. First, let me say how much I enjoyed that talk. I've been waiting to hear that for a long time. And I will also mention, Rachel, you look really natural in a faculty office with the robes behind you. It's a good look. All right. So, will the candidates for induction please turn on your audio? I mean, unmute yourselves. Okay. So it is necessary before you are accepted into membership that you take the Pi Mu Epsilon Scholarship Pledge. All right. So if you would please repeat after me. I solemnly promise.
I solemnly promise
that I will exert my best efforts.
That I will
exert my best efforts
to promote true scholarship.
To promote true scholarship.
Particularly in mathematics.
Particularly in mathematics.
And that I will support the objectives of Pi Mu Epsilon.
And that I will support the objectives of Pi Mu Epsilon.
All right. Thank you. So I will now read the name of each of the new members who is present. I think it's unfortunate that we can't be together in person, but at least that means that this might be I think it's the first time I can remember that all of our inductees were present for the induction. So trying to grab the good that we've got out of this at least. So as soon as it is possible, we will have each of you sign the roll book. We have an official roll book that's got the names of the inductees going back to, let's see, the first people to sign it in this particular book were in 1976. It's got the names of all sorts of wonderful people who some of us here remember. Many of them have gone on to really wonderful things, like, giving induction talks at, there's Dr. Susie Valley. Oh, this one's kind of cool. In 1996, we inducted someone named Lynn Martin. And Lynn Martin, you might she's now president of an extremely successful data services firm, and she's also a member of the board of trustees of Manhattan College. The point here really is that the people who've signed this book are some of the most successful alumni who we have. And the fact that you're joining the ranks of these people says a lot about you, and it tells us a lot about where you're going to go. So we're pretty excited. Anyway, also, if you have not done so, please try to stop by and see Dr. Jura to get your certificate. Okay. All right. So who do we have? We have Sean Abraham this year, who's a mechanical engineering major, who's completing the concentration in applied mathematics. That's going to be a common theme you will hear today. We also have Elias Owike, who's a mechanical engineering major and doing the applied mathematics concentration. Alex Castro Chavez, is also a mechanical engineer doing the applied mathematics concentration. Just to mix things up, we have Corey Curran, who is a double major in civil engineering and mathematics. We have Sydney Harwood, who is a mechanical engineering major. We have Natalie Metz, who's, I guess, technically a double major in adolescence education and mathematics. So she'll be sending us some students in the future, I hope. We have Stephen Palacios, mechanical engineering major and applied mathematics concentration. We have Nicole Raymond, who's a chemical engineer doing the applied mathematics concentration. Ryan Truen, who's a mechanical engineer. And lastly, we have Joseph Zaragoza, who is a mechanical engineer doing the applied mathematics concentration. All right. This is a great group. I know this group, you're pretty fabulous. I'm excited that this is the first time I get to do this, and it's you, because you're pretty great. All right, so back to Dr. Jura.
On behalf of the members of the New York Lambda chapter of Pi Mu Epsilon, I welcome you to membership in this community of scholars. Congratulations. Let's give our students another round of applause. You can take your audio off. Let's do a round of applause.
Yeah.
I will now conclude the induction portion of the evening by explaining the various insignia of Pi Mu Epsilon. They are all represented on the crest, which appears on the first page of the program that you should have received, which is also here behind me on my virtual background. At the top, surrounded by the fleur-de-lis, is the pin, which consists of Greek letters, Pi, Mu, and Epsilon. The center of the crest is a shield divided into 4 sections. In the upper right-hand corner is the design of the conventionalized violet, the symbol of beauty. This represents the beauty present in the development, study, and applications of mathematics. In the lower right-hand corner is the summation sign, symbolizing the discrete. And in the upper left-hand corner is the integral sign, symbolizing the continuous. In the lower left-hand corner are 3 stars, representing community, integrity, and truth. There must exist in mathematics the aspect of community, of sharing and mutual inspiration. It is through cooperation that greatness may be achieved. There is no place in science for deviation from intellectual honesty and integrity. Mathematics must be built on that firm foundation. It is a search for truths by means of logic, order, and precision, which yields powerful and useful results. The ultimate goal of every action of our society is based on the motto found below the shield in Greek, which translated means to promote scholarship in mathematics. Well, that concludes the induction ceremony. Let's have one more round of applause for our new inductees. And let's pause for a moment so we can take a screenshot of our new members. I'll now do a screenshot. Smile. There it is. Did you close your eyes? You want to do another one? One more. All right. 1, 2, 3, cheese. All right. Thank you all. Thank you all very much for attending. Thank you to the folks watching the live stream at home. Please stay healthy and safe. Take care, and we'll see you.